Hi, everybody. Thanks for coming. While my slides come up, let me just tell you a bit about what I'm going to talk about today. I'm going to talk about whether we should redefine statistical significance. And I'm going to, and I would like to echo some things that Deborah Mayo touched on. And I want to say that the choice of how we think about statistical evidence is not actually determined by our statistical theory. It's something that's deeper than that. And I've never met any scientists who didn't think about statistical evidence in multiple ways, including an error statistical way. Often I find that good students in my classes will, if I'm teaching Bayesian statistics, what they'll do is they'll do a simulation and they'll say, but in this case I can find, even though the null is true, I can find strong evidence against it. And I know that they're sort of thinking about statistical evidence in multiple ways. You can see it. And I've never met a scientist who didn't think about statistical evidence in both Bayesian and frequentist ways. So let's see. All right. So let's first talk about the relationship between science and statistics, because we often get hung up on significance testing, but actually statistics, of course, we all know this, is much broader. It's a highly contextual set of problem-solving tools for thinking about things like research design, data summary and visualization, thinking about fallacies and paradoxes that can cause you to come to the wrong conclusions, the wrong scientific conclusions, these sort of things. Statistics is really much broader than significance testing, but significance testing is a lot of what we talk about, and it is important. So to think that it's dropped off the list of important topics is at least concerning, I think. I say this even as a Bayesian. The basic logic underlying significance testing, that is that you wouldn't want to find strong evidence against, to often find strong evidence against a hypothesis that is true, that basic logic, we need that significance testing logic when we think about scientific results. So let's talk about null hypothesis significance testing that we can distinguish from the logic of significance testing proper. It's often abbreviated NHST. This is sort of the scientific hammer that a lot of scientists use in interpreting their data. And it comes from a sort of bastardization of classical significance testing logic, in which you focus on a single statistical hypothesis, a single effect, a single criterion for existence of an effect. That is, you don't think of the effect in a broader scientific context. You just look and see whether that p is less than 0.05, and there you have it. And as Mayo mentioned, statistical rejection is actually mistaken for theoretical support. And this is all problematic. All of it is problematic. But this is something that's distinct from significance testing. So thinking about what we call the replication crisis, we have a lot of these big replication attempts. So in my own field of psychology, we have the reproducibility project psychology, where they took 100 studies and they attempted to replicate them using similar methods. We have many labs projects where lots of labs collaborate on single questions to try to see whether they can replicate them. You have large-scale replication projects by skeptics, where the skeptic will find an effect in literature and say, I don't believe this could possibly be true. And I think oftentimes it's not, and we find failures to replicate. But the replicators have the same problems as the original scientists. They will often focus on single effects, and they'll even focus on that single criterion for the existence of an effect. Is the replication significant? And if it's not, they declare a mismatch between the original and the replication. And if you look at whether, if you actually do a test for whether the effect size in the original and the replication are significantly different, you often find that that's not significant, and further, that the effect size differences between the original and the replication, the uncertainty in that difference is huge. So we actually don't learn that much from these replications. And again, we have to blame misunderstandings about significance testing. So many replications fail, but we're not actually quite sure how to interpret this. Now, in the context, in this context, we had a paper last year by a group of 72 authors, I think it was 72, or approximately the population of Cardiff was on this paper. There's a good chance that half of you are authors on this paper. So hi, I'm going to talk about this paper. Redefine statistical significance. So the suggestion was that we change the default threshold for significance from 0.05 to 0.005, right? So add another 0 in there. And there were three main arguments for this change. There was that p-values of approximately 0.05 represent weak evidence, and so this echoes something that Mayo said. And I've inserted Bayesian there because the argument was entirely Bayesian. Number two, if you use p less than 0.05 as a criterion, then this inflates the what's called the false discovery rate, or reduces the PPV in Ioannidis's terms. And argument three was that p less than 0.05 as a criterion, the result, when you use that, the results are less likely to replicate. That is, the second one is less likely to match in its significance than results that have p-values of less than 0.005. And they actually say that using a criterion of p less than 0.05 is a leading cause of non-reproducibility, and this is important. So this is the justification of the enterprise, that the use of p less than 0.05 as opposed to, say, 0.005 is a leading cause of the reproducibility crisis. So keep that in mind as we go along. Now I'm going to focus on argument one, because this was their primary argument. That is that the Bayesian evidence is weak. So their proposal, I think, is flawed for a number of reasons, and perhaps sort of the most basic is that the idea that you can declare a discovery on the basis of a significant p-value, whether you're choosing p less than 0.05 or 0.005, it encourages a simplistic view of what a discovery is. This is really problematic. It's also based, as I'll show, on restrictive, unrealistic prior assumptions. So my counter-argument is going to be completely Bayesian. And it exaggerates the role of rare p-values near 0.05. I'll show you what I mean by that. Now, there are other arguments that I will not concentrate on, but in particular the false discovery rate argument. So Mayo and I have a paper about this that I'd be happy to share with you, but I'm not going to go into that. And argument three is provable that it's true for every pair of alphas, and so it's actually trivial. So it's not an argument, unless you think that lowering alpha to 0 is the thing you want to do. I wouldn't recommend that. So let's begin our Bayesian counter-argument. So from a Bayesian perspective, there are a number of ways of thinking about how you're going to build a model that corresponds to a significance test. We can, up on the top here, we can think of two. I'm going to focus on this pretty simple case where we have, say, that corresponds to, say, a z-test or a t-test, where we have positive and negative effects. And we can think of there being two hypotheses. This distribution corresponds to a prior. We can divide the effect sizes into positive and negative effect sizes. And this one on the top I call a set of dividing hypotheses following Stevenson. So I can think about comparing or trying to decide whether my effect is positive or negative. Now I can also, you can see on the bottom left there, I can also stick a point null in there and say, okay, I have a null model, and then I can do a two-sided test against an alternative that has two sides. So I've got H1 there, and it spans the whole space other than 0. So I've got a point null and then a two-sided prior. And then I can choose to use a point null, and then I have actually two alternative hypotheses. This corresponds to two one-sided tests, my positives and my negatives, because any scientist is going to be interested in whether the effect is positive or negative, and no scientist is going to say, yeah, I don't care about whether the effect size is positive or negative, I just care that it's there, right? So this is really important, which of these three you decide to use. Now the top is sort of the canonical Bayesian way of doing it. A lot of Bayesians don't like point nulls. I'm going to leave that to you, whether you like point nulls or not, and I'm going to talk about all three of these. So let's talk about a p-value. So I've just created a very simple example for the use of, for demonstration. Suppose that we have a hypothesis, a null hypothesis, mu equals 100, and we actually want to know whether our data are consistent with the true mean being less than that or greater than that. And we sample some data. We get x bar equals 9.855, and so this is with 250 participants and a standard deviation of 15. It doesn't matter. All that matters is how the p-value is computed here, and you can see that I look at the proportion of the sampling distribution less than my observed x bar, and it's about 0.65 or so. Now, I also, if I didn't choose that hypothesis a priori, what I need to do is look at the amount of area on the other side of 100, and so my two-sided p-value ends up being 0.13 here. So that is for this particular data set, that's where we end up. Now, I'm going to do the same thing with a prior and a posterior. So I have a prior distribution that I've put in red here, and I've got a posterior distribution in blue. So this corresponds exactly to the data that I just showed you. Now, if I want a Bayes factor comparing whether my mean is greater than or less than 100, what I do is I look at the prior and I say, my prior is centered around 100, and so my prior odds are 1 to 1. Then I look at my posterior and I note that the posterior probability is 0.93, that it's less than that. So actually, as a Bayesian, I don't have any penalty for choosing one side or the other, so I don't have to do the two-sided test. And I can say my Bayes factor in favor of the effect being less than 100 is about 14. That is the change in the odds due to the data. So that's my Bayes factor is 14. Now, at this point, you should be thinking, wait a minute. What you said was the Redefine statistical significance team said that Bayes factor, or that said that p-values exaggerate the evidence. But here you're showing that I have this, Jeffries would call this strong evidence, anything greater than 10, strong evidence. And yet the p-value of 0.16, or 0.13 rather, significance testers wouldn't typically take that as very strong evidence. So my Bayes factor appears to indicate that I have strong evidence where my p-value does not. This is due to the choice of hypotheses. So depending on how I do that, I can find the evidence going either way. So let's talk about what they did in the redefined statistical significance paper. So here I have their main graph. I apologize for the small font. This is a screenshot. The important thing to understand is what they did was they took various ways of creating a two-sided test. And they put bounds on how big that Bayes factor could be against the null. And each of these lines corresponds to a different way of doing that. And so the p-value is there on the x-axis, and you can see that the p-value decreases as you move to the left here. There's the button. The p-value decreases, and you can see that the Bayes factor corresponding to those the two-sided p-values, and this is a two-sided Bayes factor, is here on the y-axis. And what they argue is that if you look at p less than 0.0 or p equals 0.05, it corresponds to Bayes factors of only between 2.4 and 3.4 for these bounds. So if we reduced the p-value to, reduce the definition of significance to 0.005, what we get are much higher Bayes factors. And that is the core of the argument. So remember, this is based on two-sided alternative hypothesis, as well as having that point null in there. Now, there's no reason for a Bayesian to do this, because a Bayesian does not actually incur any penalty for choosing the side. And as I said, a Bayesian scientist would really like to know whether that effect is positive or negative, or above the null or below the null. And so what you can do is you can choose half the prior and get a one-sided test. And you can do both of those tests and see which one has the most evidence for it. So you can, some would call that cherry picking, but a Bayesian can do this. Somebody using a significance test would have to correct their p-value for this, but a Bayesian doesn't have to. So a Bayesian can choose the side most consistent with the data and then add an evidential boost that allowing of about, for small p-values, of about 2 minus p. So it's about 2. It's very similar to the boost that you get from doing a one-sided versus a two-sided significance test. So this actually, for the cases that we're interested in, increases the size of the Bayes factors by a factor of 2, just by being able to choose the side that's consistent with the data, which we can if we're Bayesian. So what does this graph look like when we do that? Well, okay, so the first thing I'm going to do is I'm going to add a line here for a Bayes factor of 10, because a Bayes factor of 10 is what some of the authors of the redefined significance team have said is strong evidence following Jeffries. So I can say, if I want to know whether the evidence is strong, then I'm going to look at a Bayes factor of 10, because that's fair. Bayesians have said this. I don't think that there's much point, actually, in adding these labels. What is a low p-value? I don't really know. But, we're going to take people at their word and say this is strong evidence. So this horizontal line is strong evidence. And so we want to know which Bayes factors are strong evidence once we've corrected using this 2 minus p case. Once we have said that we can boost the evidence by picking the side, because this is going to change things quite a bit, and it does actually. If you look for our two-sided p-value, and I use a two-sided p-value versus a one-sided Bayes factor, because the significance tester has to correct the p-value, but the Bayesian does not. So you might think that that's unfair, but that's the way things go. So actually, for the bounds that they compute, once you correct things, you can get strong evidence from p-values of between about 0.02 and 0.03. Now this totally changes the game. Instead of talking about redefining statistical significance to 0.005, now we're sort of in shooting range of 0.05. And you've got to wonder if it's really the case that p-values between, say, 0.02 and 0.05 correspond to weak evidence. Can that really be the cause of the replication crisis? Because the best case Bayesian argument now is that, okay, so for some problems, we can use a point null. So we will evaluate the evidence against that point null. Now, different Bayesians can argue about this, and certainly you could argue whether this corresponds to what a significance test is trying to do, but let's give it to Bayesians that we can use a point null for some problems. I would say that's appropriate. But there's no reason for a Bayesian to use two-sided hypotheses because they can pick which one they want and evaluate the evidence that way. So now we're at the point where either p less than 0.03 or p less than 0.02 is the appropriate calibration, even by the argument that the team has used. But think about that. Are those p-values common unless you're cheating? Right? So their argument has nothing to do with cheating using p-values, right? So cherry picking or running until significance, this sort of thing, stopping rules. It's just about statistical significance. Are these p-values common without cheating? So let's see. So here's a graph. What I'm going to show you on this graph is a very simple t-test example. One sample t-test. Here's my sample size. I'm going to increase the sample size there on the x-axis, and I'm going to also manipulate the true standardized effect size from between 0 and 1. So, I mean, this is the only range I need. So this true standardized effect size is just the mean from the null, the true mean from the null, the difference there over the true standard deviation. And now, as color, I'm going to show you the proportion of p-values that fall in that problematic range between 0.02 and 0.05. And you notice that this goes from 0 to 0.2. So even this range maxes out at only 20% of total p-values. And this is, for these sample sizes and effect sizes, this is what it looks like. These are the proportions of p-values that you would find. It's actually quite difficult. You have to really get lucky in order to get the proportion of p-values out of the single-digit percentages. These p-values between 0.02 and 0.05 that even by the best argument are the problematic ones that are causing the replication crisis are quite rare, it turns out. So, just to summarize, I think that the arguments for redefining statistical significance, they fail. This doesn't mean that we shouldn't think about more stringent p-values, but I think that their arguments are not good ones for it. A new criterion is unlikely to help the situation. There's no general calibration of p-values to Bayes factors. Sometimes the p-value will appear to be more lenient than a Bayes factor, and sometimes the Bayes factor will appear to be more lenient, as I showed you. There's no general calibration. And I think that because of their rarity, it's really, really unlikely that these marginal p-values that are supposedly evidentially weak have caused the crisis. They just can't be a major cause of the crisis. There may be other things like p-hacking or running until significance, but it just can't be the marginal p-values. And that's all I have, so thank you.